everyone. Thank you for being here today, first of all. So the title of my work is Advancing Network Monitoring and Operation with In-band Network Telemetry and Data Plane Programmability. This work was advised by Professor Luciano Gaspari at the Federal University of Rio Grande do Sul and was done in collaboration with Kirill Levichenko from the University of Illinois at Urbana-Champaign. So let's start with the agenda for this presentation. We'll begin by introducing the motivation and context of this PhD. Next, we will present an overview of our hypotheses and contributions, followed by a brief discussion of the state of the art. We will then continue by describing each of our contributions and results in greater detail. And to conclude, we will present our final considerations, main directions for future work, and our achievements throughout this PhD. So modern communication networks operate with high performance expectations on latency, bandwidth, and availability, and so on, especially with the emergence and proliferation of new services and applications, such as, for example, telesurgery, VR video streaming, and algorithmic trading. In this context, users demand strict guarantees, which to be met require defining clear goals for network performance, the so-called service level objectives, or SLOs. An SLO might prescribe, for example, that the end-to-end delay of a telesurgery traffic has to be less than 5 milliseconds for 95% of packets, or that the bandwidth provided to a VR video streaming traffic has to be higher than 1 gigabit per second at least 99% of the time within a minute. Monitoring SLO compliance and promptly diagnosing troubleshooting problems causing violations is essential for the operation of today's networks. However, network monitoring is also a very hard task. That is because monitoring SLO compliance has its associated challenges. First, detecting violations, which involves observing the network with very fine granularity. Second, diagnosing these violations, which requires obtaining and analyzing information about many flows, which can cause substantial overhead on the network if not done wisely. And third, the problems causing the violations need to be solved quickly so as to minimize performance loss to the users and financial costs to the network operators. More specifically, we can see that there are several challenges and questions related to monitoring networks and applications effectively and efficiently that need to be tackled. Regarding optimizing monitoring quality, there are the questions of how to achieve the required granularity, how to avoid impractical overhead levels, and also finding the ideal trade-off between quality and cost for the monitoring approaches that we are using. Regarding monitoring SLOs more specifically, there is the question of what data to collect, as well as how to analyze and consolidate these data points to enable detecting and diagnosing problems quickly. Finally, and regarding meeting SLOs in the face of problems, there is the natural question of how to troubleshoot these problems effectively. For example, if we're considering hardware failures in a network, how do we reroute around these failures? Other questions are how to react to problems quickly to minimize losses, and also how to coordinate such reaction to be consistent across the entire network. Recently, we have seen the emergence of programmable networking with paradigms such as data plane programmability and concepts such as In-band Network Telemetry, or INT for short. These bring the promise of greater flexibility to program and configure forwarding devices, and also of collecting telemetry data with production packets to achieve an unprecedented level of quality and granularity. Consequently, the hypothesis of our work is that data plane programmability, along with In-band network telemetry, can be applied to monitor and operate networks with the required granularity, practical overheads, and at data plane timescales. Given this hypothesis, our work has three main contributions. Our first contribution into in our first contribution, we conducted a theoretical exploration of in-band network telemetry to understand what are the trade-offs between granularity and cost for this monitoring approach. Our second contribution, IntSight, consists of a practical system for efficiently detecting and diagnosing SLO violations via INT-based monitoring. As our third contribution, we designed Felix to enable responding to network failures at data plane speeds and describe also how other network operation tasks can benefit from its architectural design. So compared to the state of the art, our first contribution into, to the best of our knowledge, was the first work to formalize INT orchestration as an optimization problem and to design efficient heuristics to solve it. This is an important contribution since existing tools and techniques either lack the quality, the granularity, or the scalability required by modern applications and their associated SLOs. Regarding monitoring SLOs, in the state of the art, mirroring techniques do not scale to be able to diagnose violations and problems. While INT-based techniques such as TPP and switch pointer either do not consolidate data, generating very high overhead, or rely on n-hosts as consolidation nodes and distributed storage. With IntSight, we bring both data consolidation and SLO violation detection to the data plane. Finally, talking about rerouting around failures, the standard SDN OpenFlow approach has low reaction due to the intrinsic control loop delays of this SDN OpenFlow. Furthermore, switch local and tagging-based mechanisms can help speed up reaction, but have limited applicability due to lacking coordination mechanisms to act in a consistent way across the entire network. So our third contribution, Felix, brings network-wide failure rerouting coordination to the data plane to quickly react to failures using shortest paths. So now we will look into our first contribution, which is In-band Network Telemetry Orchestration, or INTO for short. This work fills a first gap left by the state of the art by bringing an understanding of the trade-off between granularity and cost for in-band network telemetry. With INT, data can conceptually be collected from every hop by every packet in the network. However, INT applicability in real life is constrained by the fact that packets have bounded space for telemetry data, that telemetry data uses production bandwidth, forwarding devices have finite packet forwarding capacity to generate monitoring reports, and analysis servers have finite report processing capacity. We know that each INT data collection or reporting action increases packet size, link and device utilization, and the load on analysis servers. Consequently, burdening every packet with monitoring all nodes in its path, what we refer to as the full assignment, is not practical. It would violate these constraints that we mentioned and also generate tremendous overhead on the network, its traffic, and the analysis servers. With INTO, we formalize the challenge of orchestrating in-band network telemetry actions as an optimization problem. The chief requirement of this optimization is covering every interface in the network with at least one production flow. There are two main factors that influence overheads in INT orchestration. The first is the number of flows performing telemetry actions, and the second is the load on each individual telemetry active flow. These two factors have competing minimization goals. So we formalized two variations of the INT problem. We call them concentrate and balance, each one minimizing one of the main factors to understand what can be achieved in terms of individual overhead minimization. Throughout our investigation into the problem, we proved that both variations are NP complete. So as a result, we designed efficient heuristics to compute solutions to them in polynomial time. Next, we will present the main results of our evaluation. Our goal here was to understand how much can telemetry flow usage and telemetry collection load be minimized. To evaluate our proposed variations, we considered problem instances based on 260 real wide area network topologies, with sizes varying from 4 to 197 nodes, and from 12 to 38,000 flows. The telemetry demands for the interfaces, or the number of items that we need to periodically collect, were chosen from a uniform distribution with values ranging from 4 to 10 items. And the telemetry capacity of the flows, or the number of items that they can collect, were chosen from a normal distribution with mean 35 items and standard deviation 5 items. This amounts to about 10% of the traditional 1500 byte MTU of networks. So first, we evaluated how strategies fare in minimizing the number of telemetry active flows. In the graph here, each point refers to the results for one network topology using one assignment strategy, which can be the full assignment, balance, or concentrate. The brown diamonds represent the full assignment, the blue circles represent the concentrate heuristic, and the green triangles represent the balance heuristic. From the results in this graph, we observe that concentrate is the best in this aspect. The number of telemetry active flows for concentrate is typically a fourth of the number of interfaces to be monitored in the network. We also observed in our evaluation that concentrate is the best for minimizing overhead on forwarding devices and monitoring servers, since using less flows results in less reports to generate and analyze. This makes concentrate the most recommended for medium to large networks, where the number of interfaces to be monitored is already very large. Continuing, we also evaluated how strategies fare in minimizing the telemetry load on flows. This graph here is a CDF of all the network topologies evaluated. The x-axis represents the mean telemetry load on flows, while the y-axis represents the percentage of topologies up to that point. From the graph, we observe that balance is the best in this aspect. Flows in a balanced assignment typically collect about 7 items, which is the mean telemetry demand in their interfaces as per our problem instances. We know that balance in our evaluation is the best for distributing the telemetry overhead among forwarding devices, links, and flows. So the individual load on any individual element is always minimized. This makes balance the most recommended for low latency networks, since this individual overhead is minimized and there's less disturbance to any packet, flow, or forwarding device or link or analyzer server in the approach. All of these results of our evaluation for concentrate and balance show the benefits of orchestrating in-band telemetry actions. Okay, next, our second contribution fills the second gap left by the state of the art. We answer the question of whether INT data consolidation can be offloaded to the programmable data plane. We propose IntSight, a system for efficient INT-based SLO violation diagnosis that consolidates telemetry data and detects the violations directly in the data. IntSight's design has four main pillars. The first is the discretization of time into sub-second fixed length slices called epochs. The second pillar is per packet network and traffic monitoring via pathwise in-band network telemetry. The third is the per epoch consolidation and conditional reporting of telemetry information by egress nodes. The fourth and last pillar is the SLO violation detection in the data plane and diagnosis in the control plane. So here we show the overall architecture of IntSight. In a nutshell, IntSight discretizes the time into epochs. The network and traffic are monitored on a per packet basis by the data plane to track their state, behavior, and performance. For example, routing decisions, contentions that may be happening, delays, packet drops, and the provided bandwidth for the flows. Each production packet is instrumented to carry essential information in a custom telemetry header. This header has its fields systematically updated through in-network computation as the packet moves towards its destination. Each forwarding device, egress forwarding devices consolidate this information temporarily in their local memory. And at the end of each epoch, deviations from what is expected from the network, such as SLO violations or contentions, are detected by these devices using all the consolidated information, which triggers the generation of reports to the control plane. Finally, the analysis servers receive and analyze the generated reports to identify the culprit traffic disrupting network operation and so enable that to be troubleshoot. So next, we will sketch IntSight's operation by way of an example of its application to detect and diagnose microbursts. Here we consider a network with 5 devices and 5 traffic flows. The red flow represents telesurgery traffic and has an end-to-end delay SLO of 5 milliseconds. While the orange flow here has a bursty behavior that occasionally fills up the outgoing queue in node 3 and severely delays packets of the red flow. So when a red packet arrives at node 1, as the ingress node for the red flow, it updates the metadata regarding the flow in its own memory and creates a telemetry header in the packet. The telemetry header contains the current epoch on the ingress node, the end-to-end delay of the packet experienced so far, the path ID that identifies the unique path the packet has taken inside the network so far, the points of contention and potential suspicion observed by the packet, and the number of packets and bits already received for the red flow during the current epoch. The fields end-to-end delay, path ID, contention points, and suspicion points are all pathwise fields, which is to say they are updated along the path of the packet, as we will see next. When node 2 receives the packet, since it's not experiencing any contentions, it simply updates the end-to-end field, end-to-end delay field with its hop delay and the path ID according to its forwarding decision. Next, when the packet arrives on node 3, since it is experiencing contention due to the burst of the orange traffic, Besides updating fields end-to-end delay and path ID, we will also mark the third bit of the contention points field to signal that a contention was observed in the third hop of the packet, that is node 3. Node 4 simply updates the end-to-end delay and path ID fields. Node 5, as the egress node for the write flow, is responsible for storing additional metadata about the flow. After updating the necessary pathwise fields, it updates the metadata to consolidate the information contained in this packet with that collected by previous packets in the same epoch. At the end of the 42nd epoch, the one that we are seeing in this example, at node 5, since the packet just shown, as well as others that were previously received, experienced high delays, makes node 5 generate an SLO violation report and send it to the control plane. Control plane servers then receive and analyze the generated reports to identify the culprit traffic disrupting the network operation. While all of that is happening with packets from the red flow, a similar procedure is carried out for the packets of the orange flow. In their case, they are marked as suspicious by node 3 because of a high packet rate during this short interval of the current epoch. At the end of the same 42nd epoch, node 5 will also generate a report to indicate that the orange flow has had a suspicious behavior during that epoch. Then in the control plane, both reports are considered alongside to identify the orange flow as the culprit of the contention and the red flow as the victim. So correctly detecting and diagnosing this microburst event. Regarding our evaluation, in this presentation, we will mainly focus on our comparison of insights, resource usage to existing approaches, considering their report rate. Nevertheless, we will also show an overview of the evaluation of insights monitoring costs. The state-of-the-art approaches considered in this evaluation are represented by mirroring approaches, TPP, which represents the classic INT approach, and switch pointer, which uses hosts to consolidate data. For the comparison, we considered 6 of the most representative networks of increasing size from the topology zoo repetita dataset. Our evaluation was conducted with prototypes built for the P4BMV2 software switch, as well as for the NetFPGA SUME board. Our code is publicly available online. Here we present the results obtained from our evaluation. In the graph, the x-axis indicates a network topology, while the y-axis indicates the report rate. In this graph for IntSight, we also show the average and maximum number of reports as bars and circles, respectively, that would be generated for a violation lasting for an entire second when a single device in the network. IntSight here was able to keep the reporting rate under 1 million packets per second in the worst case for all of the evaluated networks. These results represent 1 to 2 orders of magnitude lower rate than the best state-of-the-art approach, which is switch pointer. Regarding monitoring costs with our approach, IntSight was found to make modest use of resources. Header space usage was kept around 25 bytes for all the networks. That is only about 2% of the traditional 1500 byte MTU. Considering the NetFPGA, the IntSight P4 program for targeting it uses only about 15% of the available lookup tables and 16% of the available registers. Finally, IntSight required about a quarter of the memory available on existing programmable targets, such as Intel's Barefoot Tofino chip, to store all of the consolidated flow information in the biggest of the evaluated networks, which has 50 million flows to track. We believe that all of these results show the benefits of consolidating telemetry data directly in the data plane and conditionally reporting via special detection mechanisms. Our final contributions fill the third gap left by the state of the art. We focus here on the question of whether reaction measures can be offloaded to the programmable data plane. We propose Felix, a system that responds to network failures at data plane time speeds. First, to motivate the design of Felix, let's consider the case of rerouting around a failure in the traditional SDN paradigm with open flow. During normal network operation, the data plane forwards packets regularly. After a failure happens, the data plane detects the failure and notifies the control plane of it. The control plane is then responsible for computing new entries that circumvent the failures and for sending updates to the data plane to be installed on the forwarding devices and update the routing in the network. While the control plane is doing that, the data plane has to wait. After all the updates are installed, the data plane can finally go back to forwarding packets. The problem with this approach is that the control plane can take a long time to compute and update the forwarding behavior. And while the data plane is waiting, packets are simply falling off a cliff. Some switch local mechanisms exist to avoid simply dropping packets like that, but they are limited in their applicability, very often resulting in routing loops or other undesirable situations for some failure scenarios. To overcome these limitations with existing approaches, Felix takes a proactive approach to dealing with failures. Before any failures happen in the network, Felix strategizes in the control plane for how the network should route packets during the normal operation, as well as during possible failure scenarios. More specifically, the control plane considers each failure scenario individually and computes the alternative forwarding entries that would be necessary in each case. Both the normal and the alternative forwarding entries are then installed in the data plane. In the figure here, we show the forwarding entries necessary to forward traffic to destination node G during the normal operation of the network and during the failure of the link that connects nodes D and G. In Felix, we refer to the complete set of forwarding devices across many devices to handle a single operation scenario as a tactic. We note here that whenever the alternative next hop under a particular failure failure tactic matches the next hop during normal network operation, the respective forwarding entry can be omitted to save table space and device memory. Here we see that happening in nodes B, E, and F that don't need an extra alternative forwarding because it's the same with or without the failure of the link from D to G. So continuing our example, then whenever a failure strikes the network, the nodes local to the failure are able to transition to a different tactic and notify their neighbor nodes as well as the routing application in the control plane of the failure. In the figure here, we see that when the link that connects nodes D and G fails, both nodes local to the failure transition to a tactic that circumvents it, that handles it. The failure notifications in Felix use a custom protocol and serve as a means for the data plane to coordinate a consistent reaction to failures. In the figure here, we illustrate the nodes in the network progressively being aware of the failure by having their color changed to orange. Meanwhile, the control plane starts planning for the future, for any potential failures that may happen while link DG is still failed. The procedures illustrated in the third and fourth figures here in the slide are similarly repeated whenever new failures strike the network, helping keep the traffic always flowing. As an aside, Felix was designed based on what we call the strategy tactic paradigm, which was also conceived as part of our work. If we abstract away Felix specifics, its architecture can be represented as shown in the slide. In the control plane, our strategy algorithm comes up with tactics to deal with different network operation scenarios. These tactics are then installed by a tactic deployment manager into the data plane, which has alternative forwarding tables to store these tactics. The data plane also has a detection mechanism and a tactic transitioning mechanism to deal with local changes, while a coordination mechanism is used to enable network-wide reaction to operation state changes. We believe that this paradigm gives the opportunity to react to problems at data plane timescales. We also believe that it could be applied to other operational tasks, such as, for example, responding to SLO violations in the context of IntSight. A more in-depth discussion of this paradigm and its generality can be found in the Ph.D. manuscript. So now coming back to Felix, our evaluation for it sought to compare it to existing approaches based on the time they take to recover from failures, aka their downtime. The downtime is generally composed of 4 delays: detection, notification, computation, and update delays. For this evaluation, we considered 3 data center networks and 3 wide area networks with the number of failure scenarios ranging from about 200 to 7,000 failure scenarios, 17,000 failure scenarios. We compare Felix to the standard SDN approach, where the control plane computes and updates forwarding behavior just in reaction to failures, and a pre-compute SDN approach, where the control plane pre-computes the forwarding entries, the alternative forwarding entries, and needs only to install those in the data plane upon a failure. Again here, similar to IntSight, we developed prototypes of Felix targeting the P4BMV2 software switch and the NetFPGA board. And our code is available online. We start showing the results of the evaluation by showing the overall results for all evaluated networks and failure scenarios. In the graph here, each bar represents the average downtime for a particular failure recovery approach in a particular network. For this part of the evaluation, we also varied the average time it takes to update a single forwarding entry from 10 microseconds, from 100 microseconds to 10 milliseconds, as shown in the parentheses in the graph legend. From these results, we observed that Felix has downtime that is up to 3 or 4 orders of magnitude smaller than the SDN approaches. This means that Felix recovers from failures up to 10,000 times more quickly than these approaches. To better understand these results in the previous slide, we break down the total downtime into its four main factors: detection, notification, update, and computation delays. From these results, we observed that in the case of standard SDN, downtime is dominated by the computation delay, while in the case of pre-compute SDN, downtime is dominated by the update delay. Felix, however, takes the computing and updating delays out of the downtime equation by doing these procedures ahead of time. As a consequence, downtime with Felix fits within the data plane timescale. The results here show the benefits of enabling reaction directly in the data plane. So here we arrive at our final considerations in this presentation. Our main takeaways, considering all of our contributions, are that first, carefully orchestrating INT actions enables achieving orders of magnitude less overhead than existing monitoring approaches. Second, with IntSight, we show that data plane consolidation of telemetry data brings huge savings. And third, with Felix, we saw that data plane reaction can considerably speed up failure recovery. Consequently, we believe that the strategy tactic paradigm has shown big potential to be applied to other network operation tasks. It is our understanding that our work opens many avenues for future research. Here, we will highlight as particularly interesting the offloading of machine learning models, such as artificial neural networks, to the data plane, and also investigating how those models could be combined with the strategy tactic paradigm to help mitigate distributed denial of service attacks, as well as realize other operational tasks at data plane timescales. We deem this line of work crucial to release the full potential of data plane programmability. So regarding our main publications, as part of this PhD, we have published 4 main papers, with a 5th paper currently under review at IEEE, Transactions on Network and Service Management. One of our major achievements was getting IntSight published at ACM Connects in 2020, considering both its rigorous review process and small acceptance rate. There, we also earned the ACM reproducibility badges due to our artifacts or code being not only publicly available, but also functional and reusable by others in the community. Beyond that, our paper on Intel received the Best Paper Award at the Brazilian Symposium on Computer Networks and Distributed Systems, SBRC, in 2018. And moreover, and finally, our work has seen a continued increase in citations by the community, which gives a glimpse of the impact of our work. In addition to our main papers, as part of active collaborations with our colleagues, we have also published other 6 papers related to network programmability to both journals and conferences. A highlight for these additional publications is the Best Student Paper Award that we received at the IFIP IEEE International Symposium on Integrated Network Management in 2019. This work is the result of collaboration with many people. I can't include all of them here. But to conclude, I would like to thank everyone that has been part of my PhD journey. To break protocol just a little bit, I would like to thank Professor Luciano for his continued support on all of these years, both professionally and personally. That have helped me got all the way here. I also want to thank Professor Kirill for the opportunity to be a visiting scholar within his research group at the University of Illinois at Urbana-Champaign. I also thank you, the reviewers of this work, the panel for this defense, for your keen observations and valuable feedback that helped shape and evolve this work. And I also want to thank Martin, Marcelo, and Luis at IntSight Tech for the opportunity to do an internship with them at their internet provider company. Finally, to finish it all off, I thank my parents, my sister, my lovely wife and daughter, and God for their continued support and encouragement in this long journey. I thank you all.